I am the Mammoth Rept, Mr. Daycock, and today I'm going to be teaching you about integration by substitution. Now, integration by substitution is a more general form of our reverse chain rule that we were using last time, and it is almost exactly the same as the chain rule, but in reversed. And it allows us to integrate much more complicated functions like this. Now, before, what we were doing was we were spotting patterns, but there's no obvious pattern here. Certainly, you can see this cosine is the derivative of both signs, either the sine on its own or the sine x plus 1, but how do you work out where it should go? What should be happening with them, given what we've got here? And the answer is it's not reasonable to spot the pattern. I can tell you what the answer is straight off. The answer is going to be sine of x plus 1 all to the power of 6 over 6 minus sine of x plus 1 all over 5 to the power of 5. And you can probably see some sense of integration there. Not forgetting, of course, in the end there would be a plus c because it's integration. But how would you spot that? You can't just spot it. What we're going to do is use substitution to justify this. Oh, and let me rewrite that. If you want to check this, pause the video now and differentiate this, and you will see that you will get that function in the integral. Okay, so let's have a look at what integration by substitution is. And it's, like I say, almost exactly the same as the chain rule. What we're going to do is we're going to pick this bit here, and we're going to call that u. We're going to say that u is equal to sine of x plus 1. And that should be fairly obvious why we're picking that. Just like when we're doing the chain rule, we pick the awkward function and call it u. And that's what we're going to do here. We're going to pick the awkward function and call it u. And now we can do some swapping around. We can also see this bit here. If u is sine x plus 1, then sine of x must be just equal to u minus 1. Just a quick rearrangement. And then we're going to get, therefore we can rewrite this as the integral of cosine of x. I'm going to leave that for now. We could rewrite that in terms of sine and therefore in terms of u, but I'm going to leave it for now. Multiplied by u minus 1, which is the substitution for our sine there, multiplied by u to the power of 4, which is our substitute for sine x plus 1 dx. And now, this looks fine, this is not much nicer, but we have two problems, but they're actually going to get rid of each other. We have this cosine x here, and this dx. And this is one of the reasons why I've always been insistent that you always put the dx on the end, because it's actually relevant. We are integrating currently with respect to x. But to use our substitution, we want to integrate with respect to u. And so we need to think about what du is. And what du is in terms of dx. So we have that u equals sine x plus 1. So du by dx is going to be equal to cosine x. And just cosine x, not cosine x plus 1 or anything like that. And then, well, we want dx. So we're going to do a little bit of rearrangement. We get du is equal to cosine x dx. And therefore, dx is going to be equal to 1 over cosine of x multiplied by du. Now, we should not be splitting the fraction like this. That is a big, big no-no. But it works. And if you want to take maths further than this, there are certainly more formal ways of looking at it. But for your introduction to integration by substitution, splitting the derivative as though it were a fraction works quite effectively. It's not always going to be correct, but it is going to be correct for probably all the times that you're going to care about, unless you're going to get very deep into pure mathematics. And so now, because we have this, we know that our dx is 1 over cosine x du. I can put that in, and now I have the integral of cosine of x u minus 1 u to the power of 4 multiplied by 1 over cosine of x du. And this is why I didn't take out the cosine before, because in fact this cosine is very nicely going to cancel out. And we're left with the integral of u minus 1 times by u to the 4 du, which is equal to, well, it's the integral of u to the 5 minus u to the 4 du, and now you might be seeing where I got that answer from earlier, and that is going to integrate to u to the power of 6 over 6 minus u to the power of 5 over 5 plus c, don't forget our plus c, and then we're just going to substitute back in what u was. So our u up here was sine x plus 1, and so this is becomes sine x plus 1 to the power of 6 over 6 minus sine x plus 1 to the power of 5 over 5 plus c. I'm going to put plus c on the end there. And that there is our integration by substitution. We have successfully calculated this integral, and it is this answer here by doing a substitution. But the absolute key thing is to remember not just to substitute your x's, but also to substitute the dx as well, because that dx has to change, otherwise you will get the wrong answer. Right, so let's look at this one. This is a classic example, and it has a very odd substitution that we're going to pick, and you would not predict this without knowing it beforehand. And so very often if you're doing an exam in this regard, they will give you the substitution to use because it won't be easy. But the substitution we're going to use in this case is x equal to sine of u. And that is a very odd one, but it's going to work quite effectively. And we're going to get dx by du is equal to cosine of u, therefore. And now this actually rearranges slightly faster, so we're going to get dx is equal to cosine of u du. And now we can plug this in, and you can see why this works quite nicely. Let's call the dx, put it in blue. You're going to get the integral of 1 over, and x was sine of u, so it's going to be the square root of 1 minus sine squared u multiplied by, and we're doing that one in blue, cosine of u du. Brilliant. Now, what's going on here? Well, down here, that seems a little bit odd. It seems very awkward and not very nice, but actually it's really nice. Because what we need to remember is that cosine squared of x plus sine squared of x is always 1, regardless of the value of x. It's identical to 1. And that tells us that cosine squared of x is the same thing as 1 minus sine squared of x. And that is exactly the substitution that we need to make here. Or in fact, let's rearrange that and change that to u. Cosine squared of u is equal to 1 minus sine squared of u. And we'll plug that in there, and we will get, this will become the integral of 1 over the square root of 1 minus sine squared of u is cosine squared of u, multiplied by cosine u du. Well, the square root of cosine squared is just cosine, so we're getting the integral of 1 over cosine u times by cosine u du, which is in fact just the integral of 1 du. And therefore, our answer is equal to u. But that's not good enough, because we didn't want our answer to be u. Well, in fact, let's be clear, u plus c, let's not forget that. We didn't want our answer to be in terms of u, we wanted it in x. This is an integral in terms of x. So we need to actually return u to being in terms of x. Well, if x equals sine u, that must mean u is equal to the inverse sine of x, or arc sine of x. The inverse sine of x, which is arc sine. That's a c, not an e. Arc sine of x. And so our integral, u is equal to arc sine of x, and it's just u plus cos c. And so our integral, and this is a classic formula, this is one that's been known for quite a while, our integral of 1 minus but 1 over the square root of 1 minus x squared dx is equal to arc sine of x plus c. Okay, and one last example, just to really cement this idea. And this is a definite integral rather than the indefinite ones we've been doing before. And this is one where you either need to have had a lot of practice at these to spot the substitution, or if you're doing an exam, they might give you the substitution that you need to use. The substitution that I am going to use, and hopefully you'll see why this makes sense as we go through it, is u minus 1 squared is going to be equal to x minus 1. And now I'm going to differentiate with respect to x to obviously find out what things are on either side. So here on the left hand side we're going to get, we know because of our implicit differentiation, we're going to get du by dx in there. And on the right hand side we're going to get just 1, so that's nice. And u minus 1 squared, well, by the chain rule that's going to differentiate to 2 lots of u minus 1. So we've got 2 lots of u minus 1 du by dx equal to 1, and therefore dx is going to be equal to 2 lots of u minus 1 du by dx. Oh, sorry, just du, let's be clear there. And now let's substitute everything in. So we're evaluating the integral from 5 to 10 of 1 over 1 plus, and I'm saying x minus 1 is u minus 1 squared, so u minus 1 squared, and then I said dx was this, so we're going to multiply that by 2 lots of u minus 1 du. Okay, that's good. Now this is going to become the integral from 5 to 10 of 1 over 1 plus u minus 1, still multiplied by 2u minus 1 du. And that's going to be equal to the integral from 5 to 10 of 1 over u, because the 1's are going to cancel, times by, and let's expand this, 2u minus 2 and du on the end. And this isn't too bad. This is the integral from 5 to 10 of 2u minus 2 all over u du. I should put brackets around there. And that is the integral from 5 to 10 of 2 minus 2 over u du, which is, now let's actually evaluate that, 2x minus 2 times the natural log of u between 5 and 10. And now we just plug the 5 and 10 in. Oh, now let's be careful here. We're integrating with respect to u and I've written x here. That's definitely wrong. Let's change that. Be careful of that. If you're integrating just a constant, we need to remember that it's going to be multiplied by what we're integrating with respect to, in this case u, not always just x. But x's are still relevant, because if we go back to the very, very beginning, this is our original integral. Oh, in fact, not there. This is our original integral. And there's something we never write on integrals, but we always really should. And that isn't, we say it's integral from 5 to 10, but what is 5 and what is 10? Well, it's x equals 5 and x equals 10. And that's very, very important here, because this is the integral from x equals 5 and x equals 10. But we've got u's in our thing we need to evaluate. So we need to go back and remember that u minus 1 squared was equal to x minus 1, and work out what our two x values are, given that, well, u minus 1 squared, let's plug in, let's try out, go from x equals 5, is going to be equal to 5 minus 1. So we're going to get u minus 1 squared equals 4. That means u minus 1 is equal to 2. Now you could say, oh, but what about minus 2? Well, what we want to do here is make sure our limits are reasonably consistent. In fact, it doesn't matter whether you pick minus 2 or positive 2 or negative 2 in this case, you just need to be consistent. So we're going to go with the positive ones. And we're going to go that u equals 3. So for x equal to 5, we get u equals 3. And then we also need to try x equals 10. And we get u minus 1 squared is equal to 10 minus 1, which gives us u minus 1 squared is equal to 9. That gives us that u minus 1 is equal to 3, again being consistent here, picking the upper limit, and we get u equals 4. And so now we can evaluate this. This is an evaluated of 2u minus 2 lots of the natural log of u, of the magnitude of u, but it doesn't matter because we're being consistent here, times by between x, not x, because we just changed it and that was the whole point, between u equals 3 and u equals 4. We'll plug those limits in and we get 2 times 4 minus 2 times by the natural log of 4, and now we don't need the modulus because we're definitely dealing with positive numbers, minus 2 times 3 minus 2 times the natural log of 3. And evaluating that, that's going to give us 8 minus 6 minus 2 ln 4 plus 2 ln 3, which is going to be 2. And let's bring these together. 2 plus 2 lots of, if I'm subtracting numbers, it's going to be the natural log of 3 over 4. And that's just your log laws to ensure, if you're not sure what's going on there. Or you could even write it as 2 lots of 1 plus ln of 3 over 4. And we're done. Okay, thank you very much for watching. That is how you perform integration by substitution. Next time we're going to be looking at sort of the reverse product rule, and this is kind of the most complicated integrals we'll get as basic rules. Beyond that, there are a massive number of ways of dealing with integrals, and some people say that integration is in fact basically kind of an art rather than a science, because it is all about spotting key ideas rather than having some simple algorithm you can always follow through. So you just need to kind of spot what's going on in each case as you try and do integrals. Thank you very much for watching, and I'll see you in the next video.